recording here. Okay, so welcome to Parametric Equations. I'm not going to teach everything there is to know about parametric equations. That's impossible. But I'm going to show you how simple it really all is, and also how it's necessary. It's kind of important. Okay, so let's just actually start by solving a problem. So we don't have to be told in mathematics every meaning of everything in order to start solving a problem. That's a big misconception. When you see a new style of problem and then you're like, oh, the teacher didn't teach me this yet, I quit. You cannot do that. In fact, good teachers should present new problems all the time and let the students use their past knowledge to try to tackle at least part of the new problem. Right? Imagine if you're a lawyer, right? You go into a situation, a client comes to you and says, hey, you know, I need you to take my case and argue my case. You wouldn't just say, oh, that's not exactly the same case as Jones versus Smith, 1948, I quit, I'm not doing your case. It's like, what kind of lawyer are you? You mean you're not going to take on a new type of case? You're not going to try to apply old cases to new cases? You're just going to like look in history books for old verdicts and try to run your case the same way this other lawyer did? You can't do that, right? Nobody in the right mind would do that, but people do it in the math classroom all the time. You guys do it all the time, some of you. You see a new problem and you're like, I quit. I wasn't taught this. You have tons of background in math. Tons. Like you can at least start it. If there's a new vocab word, you can Google it, right? Okay, so let me show you a problem here. I'll bet you could do half this problem without any help at all. Here it is. Let's let x equal 3t squared and y equal 2t. And let's let t be a number between negative 2 and 2. Graph. So we are guilty of giving up before starting. We do it all the time. Let me read the question to you in case you can't read it. It says, let x be 3t squared and y be 2t. And let t be a number between negative 2 and 2 inclusive. Graph. Graph what? You didn't tell me what to graph. I gave you an xy axis. Right? How do you plot on an xy axis? You plug in, you try to find x's and y's so that you have points to plot, right? Okay. So I think most of you would at least start this problem by asking me the question, well, what's t? What's t? Because we've seen x's before, we've seen y's before, and now you're giving me t. Shame on you. Well, listen. T is a number between negative 2 and 2. I already told you that. You say, well, no. Which number? All of them. See? So what you need to do is you really need to make a table, but you need to start with t. If you don't figure out what you want t to be, you'll never know what x is. And you'll never know what y is. So let's make a table. The first column is t. It looks like we have some freedom there. We can maybe make up any t's we want as long as we stick between negative 2 and 2 inclusive. All right? Okay, so let's go ahead and make a table. It's going to look something like this. We're going to make up our own t's with restrictions. We're then going to figure out x. We're then going to figure out y. And then we're going to plot x and y. So this is just a way to organize our thoughts. You do not have to use a table. I want to. What am I allowed to use for t here? Let's see. Someone give me some numbers between negative 2 and 2.
Negative 2.
Okay. 2. 1. Okay, I put them in this order. I think you should put them in this order. I'll tell you why later. Okay? But go ahead and pick some values between negative 2 and 2. I suggest at least the integers. You can add more if you want, but you cannot go beyond these. You're out of bounds if you pick negative 3, you know. You're out of bounds if you pick 3. You have to stick between negative 2 and 2 inclusive. That's the rule. It says right here. Okay. In other words, when I reach 2, my table's done. I'm not going beyond 2. Okay, let's get started. So, let's fill in the table. Some of you are already half done with that table. Some of you are waiting for me to finish drawing my nifty lines. Go and fill it in. Show as much or as little work as you like. I like to do the first column first. That's my style. I'm going to do 3 times negative 2 squared, 3 times negative 1 squared, 3 times 0 squared, 3 times 1 squared, 3 times 2 squared. I got 12, 3, 0, 3, 12. Let's do the second column. Doubling the y's, doubling the t's to get y. Negative 4, negative 2, 0, 2, 4. Okay. My goal was to graph. I have 5 points I can plot. 12, negative 4, 3, negative 2, 0, 0. I know where that is. 3, 2, 12, 4. Let's get busy plotting. Okay, I got these 5 points. Okay, I have a couple questions about these 5 points. First of all, should I connect them?
Yes.
Why would I connect these points? Only if I believe that in between values makes sense. Okay? So, for example, between negative 2 and negative 1, was I allowed to use, could I have used negative 1.5? Was that allowed? Yes. It was allowed. I didn't do it, but it was allowed. Where do you think that point would be? Between which two?
12 and 3.
Okay, so it's kind of important to alphabetize these, I think, or at least somehow indicate where you started here. So I'm going to alphabetize all this. This is A, B, C, D, E, and if you watched my plotting, this was A, B, C, D, and E. It happened in a specific order as I plotted. So this is kind of the first time I've ever plotted points, and I felt like I needed to put order on it since the polar plots we did earlier in the year. Okay, now, if I judge that t should be allowed to be a value between negative 2 and negative 1, then I would assume there's also another point somewhere between here, between A and B, see? So since I believe all possible t's are eligible between negative 2 and negative 1, I think I should connect from A to B. In fact, I'm going to connect from A to B to C to D to E, like this. Oops, except that was my eraser tool. And I erased my point A. Here we go. We're going to connect like this.
It's a differentiable now.
Except at C. C, it's got a vertical tangent, which has no slope. Okay. So I think we should connect them. Can I connect beyond E? Can I go beyond E?
No.
I cannot go beyond E. Can I draw any more than I've drawn? No. You may not draw out of bounds. Okay? So you have to start at A, you have to end at E, no arrowheads to show that the graph goes on forever. In other words, this is not a parabola. You might think it's a parabola, but it's not a parabola because a parabola would go on forever. This is maybe a slice of a parabola, a piece of a parabola. Okay? All right, so it's very important that you have a very clear starting point and a very clear stopping point. And there's definitely a preferred orientation. Now I need you to add orientation arrows all along your curve. The mandatory elements of a parametric graph are the following. Clear start and stop points. So clear endpoints, you could say. And clear orientation arrows. So I can see them. If you draw this graph and you draw anything extra, it's wrong. If you draw anything lacking, it's wrong. If you don't put the arrows on, it's wrong. If you put the arrows in the wrong direction, it's wrong. This is not your traditional graphing. This is parametric graphing. Okay, question?
The orientation arrows have to follow the smallest number in the domain to the highest number?
Yes. So it's really important that you make your table in order, because if you make your table out of order, what's going to happen is your points are going to be out of order. You're possibly connect the dots in the wrong order, or even if you do put them in the right order, you will have the arrows wrong. So it's pretty important that you go from least value of t to highest value of t. Okay? So the way I showed you here, if you just follow this every time, you're going to be good. I mean, your graphs are going to be perfect every time. Okay? All right. There's one more little thing I should check. Now, does 3 something squared or 2 times something, do those have any, like, forbidden inputs? You know what I mean? Like, are you allowed to plug in any t you want into 3t squared?
Well, except for it has to be negative 2 and positive 2.
Well, what I mean is, are there any numbers between negative 2 and positive 2 that would not be allowed to plug in here?
No.
No. This one? No. Now, if this was like 3t squared and on the bottom was like a t minus 1, then t equals 1 would be illegal, right? That might change how I connect my dots a bit, but that didn't happen here. Every input was perfectly fine for x equation, perfectly fine for the y equation. Everybody seems happy, and everything came out nicely. So everything's connected. Yes?
Well, what happens to a graph with asymptotes, like a parametric graph with asymptotes?
If there are forbidden t values, then you have no business plugging them in, and therefore you won't get a point to plot. You also need to be careful when you connect your arrows not to connect past a forbidden point. So we won't probably see that in this case, but this year.
If like x equals 1 is forbidden, could you
If
draw,
t equals 1 is
or
forbidden.
yeah, could you draw like a hole there?
Yeah, you might be able to create a graph with a hole using parametrics like this. But we're not going to deal too much with discontinuities or anything. I'm just playing an old rule. I'm following an old rule. You don't plug in things you're not allowed to plug in. And if you're going to be connecting the dots, make sure you didn't pass through any holes or asymptotes or anything weird, right? I don't think that's happening to us here. Domains seem pretty clear to me. Okay? So notice that we start with a domain of t. That's very important. You know how sometimes we read these questions and we see this little last factor, we kind of ignore it, you know, we're like, oh, let's focus on that. You can't. You can't do anything in this problem until you've declared what t was. And then you make your table based on t first, see? All right, now, what exactly happened here? It looks like something is moving, see? It looks kind of like something's moving. And so parametric equations are used a lot in science because in science, 2 different things might depend on a third thing. You see how x depends on what t is, and y depends on what t is, right? Now x and y might depend on each other too, but in this clearly explained or clearly expressed set of expressions, it's very clear that x depends heavily on t, and so does y. This happens all the time in the real world, right? If you go around and you start looking for examples of this in nature, you'll find them all over the place. Maybe you've seen equations in your physics book that look something like this. X equals x naught plus v naught cosine theta t minus 1/2 at squared, or plus 1/2 at squared. And y equals y naught plus v naught sine theta t plus 1/2 at squared, where a in the first equation is acceleration in the x, and a in the second equation is acceleration in the y. Maybe you've seen equations like this before. Maybe you're studying a free fall problem, or a projectile motion problem, where gravity, of course, would not affect x. So there's no acceleration. Maybe you've seen equations like this. They come in pairs. They're parametrics is what they are. What this is saying is, after being told that an object was fired out of a gun at 1,500 feet per second at an angle 45 degrees, you would know that this was 1,500 root 2 over 2, and this is 1,500 root 2 over 2. And after being told you're on Earth, we now know that this is a 16, and it's negative because Earth's gravity pulls towards the center of the Earth. And after being told that you're on a 200-foot cliff, you would then know that this was 0, and this was 200. What you're looking at here are two equations that depend on the time. After all the givens are put in, you're dealing with x equals 750 root 2t, and y equals 200 plus 750 root 2t minus 16t squared. It's exactly the same thing you're looking at here. Both x and y depend on t, right? How does the scientist study the flying bullet? For these two equations, he picks a time, plugs it in. You know, time equals 0. What's going on at time equals 0? Oh, well, it's at, and then he plugs in t into both of these, and he knows it's at 0, 200, or whatever. Or he plugs in t equals 4. Do you think he would study t equals 1 million?
No.
Not for a flying bullet, right?
Both would be on the ground.
Well, but what happens to a bullet after 1 million seconds?
It's long.
Where it was intended to go, and it's there until the ballistics department finds it. Right? It happened after t equals 2, didn't it? The 2 seconds in the air, and the thing's traveled a full kilometer. So I'm sure it's done its job. So you see that time shows up in both of these, right? And you're not surprised. And time is limited, you know, for a traveling bullet. And so this is a set of parametric equations. The parameter is time, and it has meaningful constraints. Time 0 makes sense. The trigger's pulled. Time 2, pull is done traveling. Okay? So you see that t would be between 0 and 2 or something. Remember this.
For that equation, at 2, the bullet's not done traveling. Is it? Or
Maybe it's hit its target, right? Maybe it's hit its target. Is it on the
Oh.
ground? I don't know. My point is this. We're used to seeing two equations in a situation like this. But when we get into math, we think, oh man, what's this about? There's like two equations. What's going on? No, it's the same exact thing. Did I say t was time? Not necessarily. Okay? X here could represent how hyper the boys are, and y could represent how hyper the girls are, and the parameter is how many pieces of candy I passed out. Okay? So I pass out 5 pieces of candy. Boys are super hyper. There's a t squared there. The girls are sort of hyper. See? They both depend on the candies. That's a parametric situation. Okay?
just the negative candies?
And you'd have to ask what does negative mean, right? You can't have enough candies.
Are candies away?
With time, here's what you could say about this thing. I don't know what this red thing is. Maybe it's just like an ant crawling along. It looks like the ant is crawling along a parabola. And let's say t is time. T equals -2 might mean like 10 a.m. maybe. So this is like 10 a.m. This would be 11 a.m. That way this 12 represents noon, see? And this is 1 p.m. and 2 p.m. respectively. So this is the path that an ant took as he traveled, you know, between 10 a.m. and 2 p.m. That might be what this problem's all about. I don't know. I wasn't told the context of the problem, but I've got the graph drawn. So you see these graphs are more like a trajectory, and t is very much like time. You can think of it as time if you want, although it could be candies too. But it's some third outside independent element that affects both x and y. So we start the table by declaring the time. We then calculate x and y and plot. It's all very simple, really. Now, is this a parabola?
No.
It is not technically a parabola. It's not going on forever. Also, parabolas have no direction, no start, and no stop. Okay, let me ask you this. Is this a parabola? Was the ant traveling along this parabola? Is the red actually parabolic in its shape? That's a question. That's an important question. What do you guys think? Think so? How would you ever know that? Place the parabola on top of it? A very specific one at that, right? It would have to be the right parabola. Okay, let's just play around with this. Here's how not to do mathematics. Okay? Watch close. That is a parabola. Man, look at that parabola. Whew. I'll bet I could find the equation. Don't think it's one of these. I'm doing, disclaimer, I'm doing what you should not do, okay? Watch me do the wrong thing in math, okay? That's a parabola for sure. It's not one of these guys because it's going sideways. Ooh, it's one of these guys. Ah, yes. Of course it is. X minus h, yes. Ooh, vertex is at 0, 0. Beautiful. Look at that. Ooh, I don't know what A is. Ooh, I can steal a point from my table. I probably wouldn't want to use 0, 0. I'll use 3, 2. Careful here. 2 goes in for the y. 3 goes in for the x. Ooh, 4 equals 12. A is 1/3. I got it. Y squared is 4 times 1/3 times x. Y squared is 4/3 x. Even if this answer is wrong, the whole chain of logic is a house of cards. Why? Why would this never hold up in a courtroom?
Because you assumed originally that it was a parabola without proving it's a parabola, like identities. We can't subtract from one side because we don't know it's an equation.
Okay, he's right on the money. Okay, it's all cart before the horse. The whole thing. Listen, this is so important. You cannot do this in a courtroom. Every time you hear someone say, I object, either someone used this kind of reasoning or they broke a basic rule of the courtroom. Right? You can't do that. You cannot say, well, this is a parabola. Watch, I even know which one. No, you don't. You don't even know what it is a parabola yet. You see, it's all cart before the horse. You cannot make arguments like this in life. And it's becoming more and more apparent that students are going into college and doing this kind of stuff. Okay? Who says it's a parabola? By the way, it is a parabola. That's beside the point. You just provided what's called a modus tollens argument. Okay? You put cart before the horse. You prove the effect makes cause. You said that if P equals Q, then Q equals P. You use converse logic. Okay? It would never fly in a courtroom. The judge would probably pull you up and say, what are you doing in my courtroom? This isn't law. Okay? You were guilty. Therefore you did it. Yeah, but you haven't proven that you guys guilty yet. What are you doing with that? Okay, so you understand you wouldn't do that in a courtroom, but you just did it here on the paper. Now, this is the right answer. It is the right parabola, and it was traveling on a parabola. And it's this one. But the whole thing's a house of cards. So how can we revisit the problem? Let's start over. This was bad logic. What?
You knew it was a parabola originally. You could do that.
Yes, but we don't know that it's a parabola originally. Now, let's look back at the givens, right? That's where everything starts, right? You have to go with the truths that you know to be true. For example, you can certainly believe these two things at the top, right? How can we show that these two make a y squared equals 4ax parabola? That's the question. That's horse before the cart. Horse leading the cart, okay? So what we're going to do now is try to find a meaningful way to combine these two to show that it is the parabola y squared equals 4/3 x. That's much better. So what I'm going to do is say, I wish there was no t in this problem. I can eliminate t. Let's isolate t here. I'll write t as y over 2. Isn't that the same thing as 2t equals y? Okay, so I'm going to isolate t here. Then I'll take that and plug it into the other equation, because that has the same t that this one has. This is valid reasoning. You're using substitution properties, equality, other known So let me reconstruct the argument completely from a better logic standpoint. We know that x equals 3t squared and y equals 2t. We don't even need to defend it. It was given. If we isolate t in this second one, we have every right to plug this in over here. Let's try it. What happens? You put in y over 2 here. You get x equals 3/4 y squared. You conclude that it's y squared equals 4/3 x. This is the same conclusion with a valid argument. By the way, valid doesn't mean true or not true. Valid doesn't mean true, and invalid means false. Valid means okay reasoning. You can prove something's false using valid reasoning, but you cannot prove something true using invalid reasoning. It's not allowed. Okay? So this is something that gets glossed over in geometry class, okay? Because of the state standards. They were so strict when you were in geometry that you didn't get a good chance to see valid reasoning laid out for you. You might have struggled with proofs because of your reasoning skills. Most of you guys would have known that that was illegal what I did earlier. And all of you can see the soundness of this argument. We start with givens, we make a conclusion. All right? And you know the scientific method, right? You don't take your hypothesis and then start saying, okay, because my hypothesis is true, therefore all this, yada, yada. You test your hypothesis, right? And you never believe a theory completely because it's just that. It's just a theory. It's just a construct. Newton believed his laws for centuries. Everybody did. He was totally wrong. Einstein overthrew everything with his equations. And Einstein's totally wrong. You guys, his equations are totally wrong when it comes to working with certain types of phenomena like electrons. They just don't obey Einstein's equations. Sorry. You know, in every situation. The quantum mechanics ruins it all. We need new equations. We're just not ready for them yet. See? So just, you gotta throw out that evolution stuff. It's a house of cards, the whole thing. It really is. If you want to be a good scientist, you need to go back to the drawing board. Okay, let's go to another example. How about let x equals 5 cos t, y equals 8 sine t. T is a number between 0 and pi. Okay, everything on this problem is exactly like the last one until we kind of get to the end and we try to prove that we think it's a whatever. Okay? So let's get started. We're going to make a table we learned last time. Five cos t, 8 sine t, x and y. I don't think I want to use like 0, 1, 2, 3 anymore. You know? This doesn't sound good to me. I'll use 0, but I've got to somehow get to pi. And I don't want to use 0, 1, 2, 3 pi. I'm going to have trouble with that. So let's go ahead and use 0 pi over 4, pi over 2, 3 pi over 4 pi. These are more friendly anyway. And I like to do these column by column like I showed you earlier. So I'm going to go ahead and do 5 cos 0, which is really 5 times 1. 5 cos pi over 4, so that's 5 times root 2 over 2. 5 cos 1, which is just 0. I'm sorry, 5 cos pi over 2, which is just 0. 5 cos 3 pi over 4, that's negative root 2 over 2. And 5 cos pi. In other words, my x's are 5, approximately 3.5, 0, negative 3.5, negative 5. How did I know that was 3.5? Remember, I asked you to please memorize root 2 is about 1.4. Okay, I need you to memorize that. So if root 2 is 1.4, then root 2 over 2 is about 0.7. It's really close, actually. So I don't really want you using a calculator on this kind of stuff. Just think of this as 5 times 0.7, 5 times negative 0.7. Okay, let's look at the y column. Sine of 0 is 0. Cosine of pi over 4 is still root 2 over 2. Cosine pi over 4, I'm sorry, sine of pi over 2, that's 1. Sine of 3 pi over 4, that's root 2 over 2. Sine pi, that's 0. Okay, so this goes 0, 8 times 0.7, 5.6, 8, 5.6, and 0. All right, let's plot them. Okay, so let's see here. 5, 0. Let's call that point A. 3.5, 5.6. That's point B. 0, 8. That's point C. Negative 3.5, 5.6. Let's see, that's over here. Oh, that's just a symmetry partner for point B. And E, negative 5, 0. Maybe it's a parabola again. Let's sketch our curve here. Remember, you're supposed to connect the dots, but not go outside the realm of the points you've plotted, so don't go out of bounds. So definitely start at A, stop at E. Make sure it's clear that you're stopping. If you go beyond it, I have to mark you wrong. Don't forget there was this particular direction of travel. These are the orientation arrows. There we go. Now, the graph is done. Instructions said graph. But on every problem you do for this assignment, I would also like you to figure out what shape it is. You guys think that's a parabola? Looks like a parabola, right? It would be wrong to assume it's a parabola here. What we'll do instead is we'll take the givens, x equals 5 cos t, 8 equals 5, 8, y equals 8 sine t. Let's write those down. So x is 5 cos t. Y is 8 sine t. Let's see, what did we do last time? Let's go back here a little bit. Let's go back and see what we did in the last problem. I have to scroll back one slide, okay? Let's go back. See here. Let's see. Okay, I isolated t in which equation?
Or no, Y. Plug it in.
Why did I pick y, by the way? Why did I isolate t here and not the other one? Easier. Okay, so I isolate t in the simpler equation, substitute the resulting expression into the other equation. Okay, isolate t in the simpler equation, plug it into the other equation. Let's see here. Isolate t in the simpler equation. Which one's the simpler equation? Oh, okay, the first one? Let's see here. Okay, isolate t, x over 5 equals cosine t. Got it. Inverse cosine x over 5 equals t. Substitute it. Oh, yuck. Oh man, this is not working out too good for me. How about this? Where have you seen cosine t and sine t together in an old truth statement. Something you've seen earlier in the year, something that is always true, maybe on a cheat sheet or formula sheet. Cosine t, sine t, same equation, statement that's always, always true. Where have you seen something? Yes, there is an old rule that connects cosines and sines, right? So this just didn't help too much. But we do have this old rule that cosine squared of something plus sine squared of something is 1. This is just an old truth. Part of math is using old truths to do new problems, right? How can I use this today? You should wake up every morning saying, how can I use Mama's theorem today? Sometimes you don't need to, but this is Mama's theorem. Like the most famous identity ever. How can I use it right here, right now? Well, what is cosine t in this problem? What is cosine t in this problem?
1/5 x.
Good. Isn't it true that cosine t is x over 5? Isn't that true? What is sine t in this problem? There we go. What is that thing? X squared over 25 plus y squared over 64 is 1. Boy, that looks familiar. What is that? That's an ellipse. Yes, it is. So you can see why, even though this is sort of a different topic, you want me to, did you have a question? That's an ellipse, right? Okay, so that was not cart before the horse. That was perfectly sound logic. What exactly did we just show? We showed that this is not the ellipse, guys. This is your ellipse right here. What we showed was that this is some object moving along this particular ellipse. See? Okay, so your homework problem is always the same takeaways, same things to do. You make a table, you plot the points, start, stop, point, orientation, and then you try to find a way to come up with what you think that equation is. What is it traveling along? Sketch it if you want to. I did it dashed. I'll send you the assignment later and clear expectations this time. Sorry about last night. This assignment will be due Wednesday, not tomorrow.